Greetings, everyone. In this lecture, we are continuing our discussion of model calibration. In our last set of lectures, we learned that calibration is a process where you adjust the inputs, the parameters to your model until the simulated heads and flows match what you've observed in the field. And this can be done through a trial and error fashion where you manually change your inputs and run the model and iterate until you get a good match. Or it can be automated. And in this lecture, we are going to talk about how you would go about automating this process. And to do that, we use parameter estimation software. And this is basically a utility that includes an optimization algorithm that minimizes the residual error as defined by the sum of the squared weighted residuals. So there's a single objective function, if you will, based on the total error of the model. And you indicate to the utility what parts of the input you want it to change, and then it takes over and runs the model dozens or hundreds of times until it gets to a point of diminishing returns where it can't improve it anymore. And it does this very rapidly, much more rapidly than you could do by hand. And so this is a really popular and powerful way to calibrate your models. And it used to be there were a number of different utilities for doing this, but most of them have gone away, and pretty much everyone now uses a utility called PEST. PEST stands for the P from parameter and the EST from estimation. And this was originally developed by John Doherty, and it has been fully integrated in GMS. So you can set up a MODFLOW/PEST calibration exercise using the GMS interface, and then have it, you can launch it from GMS and do everything you need to do. So how do you go about doing that? Well, there are a number of steps involved in setting up and executing automated parameter estimation, and we are going to go through each of these 9 steps as part of this lecture. So step number 1, build a working MODFLOW model. You have to obviously have a stable working MODFLOW model. Now that may seem obvious, but I have seen cases where students would come to me and say, hey, I can't get PEST to run. And when I dove into it a little bit, I found out that the model itself wouldn't run with or without PEST. So you have to make sure your model's in good shape. I always recommend that you do some manual trial and error calibration to get to a good strong starting point rather than just immediately throwing it over the wall to PEST. That's really important. So you want to find a good set of starting values for your parameters. And then basically you can use PEST to fine-tune your calibration. As you do this, there's another thing I recommend. Remember that PEST is going to run your model hundreds of times. As such, you can really, if you can shave off even a few seconds from every one of those model runs, it can save you a lot of time and also make your model more stable if you have a good set of starting heads. And so the default in GMS is it uses the top elevations of layer 1 as your starting heads. But I always recommend that before you start running PEST, you copy your starting heads from a prior solution, your model computed heads to your starting heads array. And that ensures that your starting heads are going to be really close to the final heads, and so it requires fewer iterations per run. And it also makes things more stable. So how do you do that? Well, you go into the global options dialog, turn off the toggle that forces the starting heads to equal the grid top elevations, click on the starting heads button, And then inside that array editor dialog, there's a 3D dataset to grid button. If you click on that, it brings up a list of your datasets, including your MODFLOW solutions. Select the MODFLOW solution and select the head array, and then click OK, and that will copy that entire head array into your starting heads. And save that, and you'll be ready to go. Step number 2, enter your field observed data. These are your basically your observed heads and flows that we talked about in the previous lecture. And as you do that, it's good to remember that the calibration interval that you enter for these observations is used to assign the weights to the observations. Now, in most cases, I'd recommend, unless you have a good motivation otherwise, to give an equal weight to your observations. But if you want to have some of them have a larger weight, remember that a large interval results in a small weight, and a small interval results in a large weight. So that is something to remember as you're setting this up. The next step, which is a big part of this process, is to parameterize your model. And what that means is you identify the set of input values you want the inverse model to optimize. It is not realistic just to say, well, change whatever you want, change everything. You have to very specifically indicate what parts of the model you want it to control or change. Furthermore, you have to limit the number of parameters, because the number of parameters that it's changing has to be less than the number of observations. Unless you're using the pilot point method, which I'll talk about later, but in general, you have to make sure this connection holds. For example, if I have, let's say, 20 observation wells and flow measurements in total, then I can't have it change more than 20 parameters, otherwise it becomes numerically unstable. It's like having more equations than you have unknowns, or more unknowns than you have equations, I guess is the right way to say that. And therefore, what do we do? Because, for example, if we have a hydraulic conductivity array, we have one value per cell. Theoretically, each of those individual cell values could be a parameter. So parameterizing the model means that we often do something to simplify the input. And to do that, there are 3 primary methods that we use: zonation, multiplier arrays, and pilot points. So let's start with zonation, because that one is fairly intuitive. But before we get to that, let's talk about what parameters are legal to change. So this is not an exhaustive list, but these are it's a mostly complete list of the parameters. When I say legal parameters, I mean, in terms of PEST, these are the things that you're allowed to mark as parameters. And so in the flow package, this would be the LPF package, for example, hydraulic conductivity in the horizontal and vertical direction, your anisotropy factor, specific storage, specific yield for transient models. And then in source sink package, recharge flux is a big one. And then conductances, well, pumping rates, that can be a parameter. Sometimes we don't know that. We only have an estimate, and we can solve for that. What pumping rate results in the best calibration, given other constraints. And then the others that you see there. I do have asterisk by horizontal hydraulic conductivity and recharge. Those far and away are the most important and the most sensitive parameters, meaning these will have the largest impact compared to any of the other things listed here. And so that is where we typically focus most of our time and effort during the calibration phase. So let's suppose that we have our hydraulic conductivity and recharge arrays, and we need to parameterize them. We simply can't allow PEST to change each of the cells individually, so we need to come up with another approach. And one of these, as mentioned in the prior slide, is zonation. Zonation means you take an array such as the one shown here, and then you break it into zones. And so instead of having, in this case, what do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 by 9 grids, so there are 81 cell values. But if you group those into zones indicated by the colors, well, now we have 3 values. So we've gone from 81 values to 3 values by creating these zones. Of course, you can configure your zones however you would like. And often there's some logic in that. We look at different parts of our aquifer, and sometimes there are natural zones that we can use and delineate. But that, again, allows us to go from a large number of cell-by-cell parameters to a smaller number of parameters. And this is probably the most common parameterization method. This is really easy to do using the conceptual model approach in GMS. You just go into your conceptual model and you delineate polygons for your recharge and hydraulic conductivity, and each of those can become a parameter. And we will go through an exercise in class where we set this up, and you'll see it's pretty easy to do. Another option is to use a multiplier array. I don't know if you've ever noticed, but in the MODFLOW array editor dialog that we use in GMS for things like recharge, hydraulic conductivity, there's a little, at the top of the window, there's a little multiplier constant, and the default is 1. You can make that a parameter. And basically what it is, it's a multiplier that applies to the entire array. So you're basically scaling the array up or down as you change that multiplier, so that becomes a single parameter that can have an impact on the entire array. I don't normally use this very much, but it's one of the ways in which you can parameterize your model. Now, another method that is very powerful is called the pilot point method, and this is used for hydraulic conductivity and recharge only. And typically for hydraulic conductivity more than recharge. But the idea here is you define a set of scatter points distributed throughout your model domain, and then you assign an initial guess of the hydraulic conductivity at each of these points, and then you use an interpolation algorithm to interpolate from these points, spatially interpolate to the cells in the hydraulic conductivity array. And in this case, each of the pilot points becomes a parameter. So the number of parameters you have is a function of how many pilot points you use. And you can just use a small number or a large number. But this is a very effective way to parameterize your model. It often results in a very good fit between your computed and observed values. And we are going to dedicate our next lecture to this pilot point method, so we'll talk more about that as we move along. Now, regardless of which of these techniques you're using, we typically use to indicate, for example, where your zones are. We use something called a key value. It's a term we use in GMS terminology. And basically, it's a value that you use that you'd not expect to find in the input. So for example, if I have my hydraulic conductivity array, and I have it defined through zones, I could put these negative values in, and then when we do map to MODFLOW, these values are assigned to the individual cells in the hydraulic conductivity array. And then later, we reference these values as part of a latter step of parameterizing the model. And the idea is, the reason we use negative values is there's no such thing as a negative hydraulic conductivity. And so when we're looking, there's a point in the process where we try to determine where our parameters are, and we just scan these arrays for negative entries. And if we have a whole bunch that are marked -60, then we know, well, that's a parameter labeled as the -60 parameter. And it's a convenient way to help you set this up. So, because in the next step, step number 4, once we've entered these key values to indicate where our parameters are, we go into the parameters dialog, and there's a button in the lower right corner, initialize from model, and when you click on that, what it does is it scans through your inputs and it looks for negative values where you wouldn't expect negative values. Typically you don't have a negative recharge, you don't have a negative hydraulic conductivity, and then based on those values it builds this table of parameters. So you'll notice that we have a -30, a -60, a -90, -120, and this goes back to this image here. And since those key values were found in the hydraulic conductivity array, it creates a hydraulic conductivity parameter for each of those. And then we have 3 different parameters based on these 3 key values in the recharge. So again, the function of these key values is to indicate the location of where we want the parameters and how that zonation is defined. And once we have that, we can build this list. And once we build the list, there are some things that we need to edit. We have to give a minimum and a maximum value and a starting value for the parameter. Now these starting values here are very detailed. This probably comes from a final solution after the optimization process. Normally you don't have that many digits, but so you give an initial guess that's your parameter value. You bracket it with a min and a max, so during the optimization process PEST will not go below the minimum or above the maximum value. There's a log transform toggle. For something like hydraulic conductivity, it makes sense as PEST is changing the values up and down. It does that. It scales it on a log scale as opposed to just a regular linear scale. And you can do both hydraulic conductivity and recharge this way. The rest of those parameters, B-scale, tide, clusters, those are more advanced topics. You don't need to worry about those now. And there's a more compact version of this dialog. If you turn off the show all columns, it compresses the number of things that you see. Another one that's important on the left, there's this parameter estimation solve toggle. If you uncheck that, then it doesn't, for example, let's suppose I uncheck that for the HK30 parameter. What that means is it would hold that value constant while it varies the others as it attempts to find an optimal parameter value. Once you parameterize your model, you can actually use it in multiple ways. You can do what's called a forward run. A forward run means it takes the starting values in this column in this list and plugs them in to where the key values are. It substitutes each of these starting values for the associated key value, and then just does a normal MODFLOW run. This is what we call a forward run, and even if you're doing manual calibration, it can be really beneficial to parameterize your model. Then, if you want to do a series of runs, you just go back to this dialog and change your starting values. You don't have to go to the conceptual model and double-click on polygons and enter things and do map to MODFLOW. You simply change things in this table and save and rerun your model, and you get a new solution. So it's a very efficient and convenient way to modify your inputs once you've done this parameterization, just to do a normal forward run. Or you can do an inverse run. So when we're running PEST to solve for the optimal parameter values that minimize the residuals, we call that an inverse run as opposed to a forward run. It's an inverse run because we give it the heads and flows as part of the input, and it solves for the what we would normally call the input parameters. And this can require a lot of runs. So at each iteration, at each PEST iteration, it goes in and for each it holds all of the parameter values constant except one, and then it'll move it down or up a little bit, and then it'll see by reducing a parameter, what does that do to the error? Does it make it better or worse? And then it does it to the next parameter and then the next one. And so for each PEST iteration, if I had, say, 20 parameters, it would run the model 20 times, sometimes 40 times. Sometimes it tweaks it once per parameter and sometimes twice. And then it comes up with a new set of values and then does another run. So at each PEST iteration, it outputs a new set of parameter values for each of the parameters you've defined. And then finally, you can also, if you're doing a stochastic simulation, which we'll cover later, you use the same process to parameterize your model. Then there's kind of a randomization process you use to change your parameters. Once you've parameterized your model, you can edit your PEST options. There's some global PEST options. Most of these you will not change. The default value is typically fine. You can turn on parallel PEST if you want, and if you have a multi-core machine, which most computers have that these days, and basically it'll send a separate MODFLOW run to each of the cores on your machine. And there's actually a way, if you explore it in more detail, we're not going to cover it here. There's a way you can set up a network of computers so that there's like a master and then a number of slave computers, and it farms out the models to each of the individual computers. So if you have a really big model that takes a long time to run, you can harness lots of computational power. I've seen people do this on using the Amazon cloud or Microsoft Azure cloud, but that's an advanced topic. There's also this thing called single value decomposition, or SVD assist. If you have a large number of parameters, you might want to turn this on. We'll talk more about this when we get to the pilot point method. But in general, you don't need to change anything here. Step number 6, this is also optional. You can edit group weight multipliers. If you look at your output and your head residual is changing but your flow residual is not, you can use this to give a greater weight to your flow residuals. The defaults are 1, meaning everything is equally weighted, but it's kind of a global weight that so if you reduce a value or increase it, you can reduce or increase the weight assigned to that category. Normally you don't need to do this. In most cases the default values are fine, but it's something to think about. Okay, at this point, once you have it set up, you save and run the model. And by the way, I did skip something. In the global options in the GMS, there's an option to turn on parameter estimation. You have to actually turn that on in order to use PEST. But if you turn that on and save and run your model after you parameterize it and set everything up, this is what the model wrapper, the model console looks like when you're running in parameter estimation mode. And so in the upper left corner you have a plot that shows the global error versus iteration, and that should be it should go down and then just get smaller and smaller as you go. On the upper right, iteration number 1 is your original starting values of your parameters and the initial error, total model error found with those parameters, and then after it's done this whole cycle of running the model at least once per parameter, you go to the next PEST iteration and the total error is reduced and it has an improved estimate of each of the parameters. And so as these continue, you'll see the total error goes down and those parameter values are incrementally improved to result in that lower error estimate. Then of course you get your standard MODFLOW output at the bottom. At some point, when it reaches a point of diminishing returns, it will stop once it cannot improve it any longer. There are cases though where it takes a long time and it has a really low error, but it keeps trying. In that case, there's a little button down here that's called Stop with Statistics. That basically means that's good enough, just stop and output the results. Otherwise you can wait till it's done and click on the close button. And once you click close or stop with statistics, it will then read in the solution into GMS for visualization. Now, what it reads, we got to be careful here. What it reads in is the heads and flows and the simulated values at each of your observations. The total errors are then read in and displayed. You can right-click on your solution and look at the total errors as we discussed last time. Your calibration targets and plots are all updated, and then of course you right-click on the solution to see the global error norms. And then in some cases you look at it and say, well, that did pretty well, but I think I can do better. And you might want to go back and try a new set of starting values. PEST does not always give you the best solution. If you've ever studied optimization theory, you may have learned that it's very sensitive to the starting values you give it. And sometimes you can get what's called a local minimum. So it gets to a point with the parameters where it can't improve it anymore. And so it stops. But if you were to give it a different combination of starting values, it could then progress to a better solution that gives you a lower error. And so unless you have a really low error the first time, I would always recommend going back and trying some different starting values to make sure that you have what we call the globally optimum solution, globally optimal solution. Now at some point you may decide that you're done, and at that point you need to import your optimal parameter values. So part of the output for PEST is a file that contains a list of the final optimized parameter values. And those are not automatically imported to the model. You have to explicitly tell it to load them in. And you can do that by clicking on the Import Optimal Values button. And what it does, it reads that file and it puts those optimal values into this value column, which normally holds your starting values. And again, unless you click Import Optimal Values, it will simply preserve your original starting values from one PEST run to the next. And then once you've done that, you can go back to the Global Options dialog, change your run option from inverse mode to forward mode, and then from that point on, your model is still parameterized, which is totally fine, and you can then start using it as a predictive tool. So it's actually very easy to set up and run. It's a very powerful tool. A few other things we need to talk about though before we attempt it. One of these is inverse model stability. it's not uncommon at all for PEST to crash or fail to converge. And the reason is that MODFLOW itself must be able to converge in order for PEST to run successfully. And remember that PEST is changing your input values, and sometimes it could be that your starting values are bad for your parameters, or as it's changing them, maybe it selects a parameter value that results in dry cells or the model not converging. So sometimes, just to make sure PEST has a better chance of converging at each time it runs MODFLOW, you can increase the maximum number of iterations for your solver or decrease the acceleration parameter. Makes your overall PEST iteration take longer, but sometimes that's necessary. Because if you do have cells go dry, it causes an irregularity or a discontinuity in the objective function. The objective function is this global error, the sum of the squared weighted residuals. And it treats that as a mathematical function, and it calculates gradients. And if that's not changing smoothly, if it has discontinuities in it, it may not be able to converge. And so this can be an issue with some models. It just depends on the model. Another thing that we talked about last time was model uniqueness. We mentioned that in some cases you can have a model that's calibrated, but it's meaningless because it's not a unique calibration. There could be other combinations of parameters that parameterize it equally well. It turns out there's a numerical way to analyze that. It has to do with the sensitivity of the parameters. And so if you, after running PEST, if you look in the folder where the MODFLOW files and the PEST files are stored, and by the way, all the PEST files are included in the same subfolder with your MODFLOW files, there's a file that ends in MTT. So whatever your simulation name is, .mtt, and if you look in that, it has a set of eigenvalues listed at the bottom. And if you compare the ratio of the maximum to the minimum eigenvalue, if that's larger than about 10 to the 8th, then your model is non-unique. This is a rule of thumb that John Doherty came up with, the author of PEST, and it seems to work pretty well. So this is what the file looks like. This is, in this case, there's only 7 parameters. Often you have much more than this. But if you look through that, and in this case, the maximum eigenvalue would be the one on the right, 8.0549 e to the minus 4. The minimum one is the one on the left, 4.755 e to the minus 9th. And so if you mainly look at the coefficients, or the exponents there, so that's about a factor of 10 to the 6th. Which is less than 10 to the 8th, so it's unique, not by a lot, but it is unique. It's common for this number to be on the magnitude of 10 to the 3rd or something. But if it's larger than that, that just means that there are numerical indications that your model's not unique. So this is a really good rule of thumb to remember. Another thing that's very useful after running PEST is to look at your parameter sensitivities. This gives you some really important insights to your model. So for each of your parameters, how much does the parameter affect the model error? It turns out that some parameters have almost no impact on the model error, and some have a really large impact. As I mentioned before, recharge and hydraulic conductivity typically have the largest impact, but which of your recharge zones and which of your hydraulic conductivity zones? So if there's another file output by PEST is a .sen file, and it contains a summary of the parameter sensitivities, the relative sensitivities. And so a high value is a high sensitivity, a low value is a low sensitivity. And it turns out that you can actually, instead of looking in the file, there's a way to plot these in GMS so that you can just see visually on a chart which are the relative sensitivity. So in this case, HK120 and HK60 had a very low sensitivity, and Recharge 150 had the highest sensitivity. The way you generate this plot is you click on the Create Chart wizard, the plot wizard, and then you just pick parameter sensitivities and then click Finish, and it will generate your it automatically knows if you just completed doing a sensitivity, or excuse me, a PEST run, it will select the right file for you. I can't remember if it picks the file or it has you search for the file. Either way, it then will generate your parameter sensitivity plot, which can be really useful. So that's it. Again, seems like a lot of steps, but several of those were optional. It's quite easy to parameterize your model, set up your parameter list, and run PEST, and you'll find it's a really powerful and effective way to calibrate your model.